In this video, we're going to solve some problems using Kirchhoff's voltage law. Now the question reads, find VBE and VDA in the circuit. So they give us a circuit diagram and they want us to find the voltages across the points BE and across the points DA. Alright, so let's start with the first one, VBE. Now we should remember what Kirchhoff's voltage law states. Kirchhoff's voltage law, also known as KVL, says the total voltages of each component around the loop must equal to 0. So the first thing we must do is identify the loops we have for the voltage VBE, which is going to be this wire right here, right? So because we want to find the voltage VBE and we have this wire VDA and it's overlapping, I'm just going to kind of scorch it out, right? So I'm just going to act like this wire isn't here for the time being. So try to visualize that this wire isn't here. So we just have this circuit with this wire. So this is like our only diagonal, right? Now when we look at this, we know we have 3 total loops, right? We have this loop, we have this loop, and we have an outer loop. So let me label this. I'm just going to label this loop 1. This is loop 2. And we have an outer loop that's going to be loop 3. So they want us to find the voltage across these 2 terminals, B and E. Therefore, we're just going to have to use KVL at one of the loops. Which one do you want to use KVL at? Well, here's the thing. It doesn't really matter. Why? Because we know the voltages across each component for loop 1 and for loop 2. So any one you choose, you're going to get the correct answer, right? Now, before we continue, I would like to point out something. Because we have this wire here, and we're measuring across these 2 terminals, we must have a polarity. We must know, if we was to grab a voltmeter, where the positive terminal is and where's the negative terminal. So when we look at this, we know the first letter of this subscript is going to be where the positive terminal is going to be. So for this one, we know where B is, that's going to be the positive terminal, and where E is, that's going to be the negative terminal. So let's do KVL. I'm going to do KVL at loop 1. Like I said, you can do KVL at loop 2 because we know this wire also is a part of this loop, which we labeled as loop 2. So I'm going to write this now as KVL at loop 1. I'm going to start right here at this 6-volt source. So because we're entering from the positive terminal, I'm going to write it as a positive voltage. So I have 6 volts. Then as we go around, we have 8 volts at that resistor. Then we have minus 6 volts at the top resistor because we're entering the negative terminal. And finally, we're going to end it with plus the voltage across that wire is just going to be the voltage VBE. And we know all of that should equals 0. That's what Kirchhoff's voltage law states. Now let's start to simplify this. 6 minus 8 minus 6 is going to give us negative 8 plus VBE equals 0. Therefore, VBE equals 8 volts. So this is going to be your answer for part A. Like I said, if you want to do KVL at loop 2, by all means go right ahead. Now I'm just going to clean up the circuit and remove everything I added onto the circuit diagram. Alright, now let's do part B. We know part B wants us to find the voltage across the terminals D and A. Okay, now we know that's going to be this wire right here. So because we know it's this wire, I'm just going to shade out. That way we can ignore the wire VBE. So let me just shade that one out. So you have to act like it's not there, right? Now remember, we're just trying to measure across those terminals. So this wire VBE doesn't really matter. It doesn't affect the circuit at all. All we're doing is measuring the voltage across these terminals. So we just put in this wire just for the sake of performing KVL. So we can kind of scorch that out, right? So now let's find the voltage across the terminals D and A. We know what we should do is we should write down the polarities. So because D is going to be the first letter, we know the positive terminal is going to be by D and the negative terminal is going to be closer to A, right? It's going to be by A. Now when we look at this, once again we have two loops, right? We have this loop right here, call this loop 1, and we have this loop, I'm going to call this loop 2. And we can use any of these two loops to find the voltage VDA. So we have 3 loops in all because we also have an outer loop, right? So let's do KVL at loop 2. I'm going to say KVL at loop 2. So notice, the loops have changed. What we had for loop 1 for part A is not the same thing as what we have for loop 1 for part B, right? For this one, I'm also going to use loop 1. I'll say KVL at loop 1. Now notice, what we had for loop 1 for part A is not the same thing what we have for loop 1 for part B. It is going to be different depending on the terminals they want you to measure the voltage across, right? So when we start to analyze this now, I'm just going to start at the source. We have a 6 volt source. It's going to be positive, right? Minus 8 volts across that resistor. Then we're going to come down this way. So we're going to have a minus VDA. Then our final voltage is going to be a minus 4 volts across the bottom resistor. And all of that should equal 0. Okay, now let's start to simplify this. We have 6 minus 8 minus 4. That's going to give us negative 6 minus VDA equals 0. We want to get VDA by itself. So we have VDA minus equals positive 6. Therefore, the voltage across the terminals D and A is going to equal negative 6 volts. So this is going to be our answer for part B. You can perform KVL at loop 2 for the voltage across the terminals D and A, and you should also get negative 6 volts. So these are our 2 answers for this particular problem. Okay, let's work another example. So this question says find Vx and Vy in the circuit. So where is Vx and where is Vy? Well, we know this is Vx and this is Vy, and they give us the polarities of each of the voltages they want us to find. So now what we should do is, we know we're going to be using Kirchhoff's voltage law, so let's label each loop. I'm going to label this one loop 1. I'm going to call this loop 2. And when we look at this, we have a situation here where we can take this as one big loop, right? But I want you to pay very close attention to something. So we know the voltage across these 2 points. So right here and right here, we know the voltage. That's going to be 12 volts. So just imagine, even though that isn't a wire, just imagine we have a wire right here. That's going to be separating this side and this side, right? They didn't draw it in our original circuit, but we have to imagine that because we know the voltage across these 2 points. They give us that voltage. So you don't have to write this wire here, but just imagine a wire being there, okay? I'm just going to actually erase that because I want you to really try to visualize that, right? Now we know we're going to have a loop right here. Because of that wire, I'm going to label this loop 3. And we're also going to have another loop right here. I'm going to label that loop 4. Now, of course, you have an outer loop, right? Which is going to be this entire thing right here, which can be labeled loop 5. You can also say that this loop right here is loop 6. And the entire circuit is loop 7. But that's enough loops for now. Let's just start to write the KVL equations for each loop, right? So for loop 1, let's write our KVL equation. KVL at loop 1. We know this is loop 1, so let's start right here. We have a plus 6 voltage, so we have 6. Then as we walk around, we're going to enter the positive terminal here. So it's going to be plus 6. Now, once we get to this resistor here, we know it's going to be a voltage across this resistor. Now, in this particular problem, they did not label this voltage, which means we now have to go and assign a voltage for this particular resistor, because we know it's either going to have a voltage drop or a voltage rise. So what I'm going to do is I'm just going to label a voltage in this particular situation. I'm going to label this voltage VA, right? And I also have to go and assign the polarities. So I'm going to assign the polarities to be negative, plus. So it's a voltage rise. Now when I start to reanalyze the circuit, I know I'm going to be walking into the negative terminal of the voltage across this resistor. So I'm going to write minus VA equals 0. So let's start to simplify this now. We're going to have 6 plus 6 is 12 minus VA equals 0 minus VA equals negative 12. Therefore, VA equals 12 volts. So this is our answer across this resistor. Now, the question didn't ask us to find that, right? But doing these Kirchhoff's voltage laws, we don't really know what we're going to get. So it's just a matter of keep writing these equations and seeing what we can find and then going from there. So for this particular loop, we were able to find the voltage across this resistor, right? It might be helpful later on. So let's just circle that. Alright, so remember, we're still trying to find the voltage Vx and Vy. So let's do KVL at another loop. I'm now then going to write a KVL equation at loop 2. You can do it at loop 3 or loop 4 or even the other loop. It's really up to you, but I'm just going to choose loop 2, right? I want to show you something. Sometimes you just have to write these equations and just see what you can do with them. Sometimes you're able to work with them, sometimes you're not. But that's the process of writing KVL equations and analyzing these circuits. So I'm going to write KVL at loop 2. I'm going to start right here. I'm going to go into the voltage source at the negative terminal. I'm going to have negative 6. Now as I start to come around, I have this resistor here. Once again, they did not label the voltage across this resistor. So we're going to have to assume what that's going to be. For me, I'm just going to assume it's a voltage rise. So I'm going to say this is going to go from negative to positive. And I'm just going to label this voltage VB. So I'm going to have VB, right? Now as we walk around this loop, we're going to enter the negative terminal. So it's going to be minus VB. And then we have minus 4 equals 0. Now in this equation, we only have one unknown variable. So let's solve for this. Negative 6 minus 4 is going to give us negative 10 minus VB equals 0. Minus VB equals positive 10. Therefore, VB equals negative 10. So once again, this is not a part of the question. They want us to find Vx and Vy. But now that we know the voltage across this resistor, it might be helpful to us, right? It might be helpful. So I'm just going to circle it. Now let's find the KVL equation at loop 3. Now I think this is the most trickiest part of this. We have to be able to notice we have two different loops here, right? We can just draw it in a wire, like how we did in the first introductory video. We can just draw in a wire here that's going to separate these two loops, okay? So I'm just going to do a KVL equation at loop 3. Let's start here, right? So we're just going to start at this resistor. And we're walking into the positive terminal of the voltage across this resistor. So we're going to have a positive Vx. I'm just going to write it as Vx. As we come around, we enter the positive terminal for the voltage across this resistor, which we labeled as VB. So we have plus VB. Now before we move on, I want to point out something, right? we cannot change the polarity of this voltage. Therefore, we cannot write this as minus plus. It won't work that way. Once we draw in a voltage and we have its polarity, that is going to have to stay constant throughout this entire problem. We cannot change that polarity anymore. We cannot say now that this is minus plus, because that's going to throw our passive sign convention all the way off, okay? So once you have something, you stick with it and you keep it going. Everything is going to work out in the end, right? So we label this minus VB plus, right, as a voltage rise. And when we look at it, in loop 2, it's a voltage rise. But in loop 3, is actually a voltage drop. But it doesn't matter. Everything is going to work out like I said. So let's continue the problem. Now, our last voltage for loop 3 is going to be this 12 volts right here. And we're entering the negative terminal. So it's going to be minus 12 equals 0. Now, when we start to solve for this, now you might look and say, well, there's nothing I can do. Well, there is something you can do. Why? Because we just found the voltage VB, which we know is going to be negative 10 volts, right? So now what I'm going to do is I'm just going to substitute in that negative 10 for VB. So I can write this as Vx. We know we're going to have plus negative 10 minus 12 equals 0. So let's start to solve for this now. We can say Vx negative 10 minus 12 is going to give us minus 22 equals 0. Now we can take this minus 22 over to the next side. Therefore, we can say that Vx equals 22 volts. Now, this is one of the answers they wanted us to find. So we know we have successfully found Vx. Now, they also want us to find Vy. So we also have to look out for Vy. We know Vy is here. So now we can do a KVL loop at loop 4 if you want to. Or you can take KVL at this outer loop at these points. So you have 2 or 3 options, right? It's really up to you on where you want to go with this. But for me, like I said, I'm always going to do KVL at the loop with the least amount of components, right? So I'm just going to do KVL at loop 4. So I'm going to say KVL at loop 4. We're going to have now, as we continue to walk around, it's going to enter this negative terminal, which is going to be minus Vy. So we're going to have minus Vy. As we continue to walk around, we're going to have plus 12 equals 0. Now, when we look at this, we only have one unknown variable, which is Vy. So let's solve for that. We have negative 6 plus 12. That's going to give us 6 minus Vy equals 0. We can take the 6 over to the next side. Therefore, negative Vy equals negative 6. So when we solve for this, we can say Vy equals positive 6 volts. So this is going to be our answer for Vy. Now that we have this, we have successfully solved this problem. We found Vx and we found Vy. Of course, we also found Va and Vb, but this was just something we had to find, or this was just something that came about from us doing KVL at different loops. When using Kirchhoff's voltage law, some of these problems are not as straightforward as you may think. Sometimes you just have to do trial and error to see what you can find that might be able to help you later on. So now that we answered this question, let's do another example. So this one says find VAC in the circuit. So this question says find VAC in the circuit. So let's find where VAC is. 1 second. Let me add in where C is going to be, and that's going to be right here. So we know VAC is going to be this entire line, right? So this entire wire right here is going to be VAC. By the way, before we even do this problem, I would like you to know that there are multiple ways to solve this problem, right? I know at least 2. We can do KVL, or we can just look at the voltage in this wire, right? You know what? For the sake of time, I'm actually just going to really look at the voltage across this wire. So I know we have from A to B, we have a 4-volt voltage. And because we're walking from A to C, right? I'm going to go this way. Therefore, I can say VAC equals 4 volts plus, because we're also entering the positive terminal of this source, we have 3Vx. So we have 3Vx. Therefore, we just wrote down the voltages for VAC, right? Now, we have this Vx here, which is an independent variable. So the voltage of this source is going to depend on the value of Vx. And when we look around our circuit, we have the value of Vx, which is going to be this resistor right here, which is actually 2 volts. So we can write this as VAC equals 4 plus 3. We know Vx is 2 volts, so we can write 2. When you start to solve for this, VAC equals 4 plus 6. Therefore, we can say VAC equals 10 volts. So this is our answer for this problem. Okay, I think this one was pretty straightforward for the most part. Let's move on to another question, right? It says find VAD and VCE in the circuit. So they want us to find the voltage across A and D, which is these 2 points. So let's draw in a wire at the points A and D. And let's label it VAD. Now we know the polarity is going to be positive for A, negative for D. So now when we look at this, we have 3 loops in all. We can call this one loop 1. This is loop 2. And we have a 3rd loop that's going to be the outer loop, right? Now which one would you like to perform KVL? So I have 2 options, right? I can either do KVL at loop 1 or KVL at loop 2. I'm actually going to do it for both, just so you can see it's possible to do it at both loops and get the same answer. I'm just going to do KVL at loop 1 first. I'm going to start here. So when I walk this way, I'm going to meet the negative terminal first. So I'm going to have a negative 1 voltage. Then as I go up, I'm going to meet this negative terminal next. So I'm going to have a negative 4 Vx. And as I continue to go up, and now I'm coming down this way, I'm going to meet this positive terminal. So I'm going to have plus VAD equals 0. Now we have 2 unknowns, right? And we know this is a voltage dependent voltage source. So we need to know the value of Vx to find the value of this source. Now when we look at this circuit, they actually give us the value of Vx. They tell us that Vx equals 2 volts. Therefore, everywhere we see Vx, we can just write 2 volts. So in our equation now, we can simplify this to be negative 1 minus 4. Instead of Vx, we're actually going to write 2 plus VAD equals 0. Now let's start to simplify this. We have negative 1 minus 8 plus VAD equals 0, which is going to give us negative 9 plus VAD equals 0. Therefore, we can say VAD equals 9 volts. So this is going to be the answer for this problem. So we took KVL at loop 1. Now let's do KVL at loop 2. I'm going to write it out. KVL at loop 2. Alright, we're going to start at this resistor right here. So we know we're going to walk into a negative terminal. So we have negative 1. Then as we walk into another negative terminal. And that's going to be Vx. So we can just write this as minus 2. Because we know Vx equals 2. So we wrote minus 2 plus 12. And our last voltage is going to be minus VAD. And all of that equals 0. Okay, so now let's start to simplify this. -1 minus 2 plus 12 is going to give us 9 minus VAD equals 0. You can carry the 9 over. It's going to give us negative VAD equals negative 9. Therefore, when we solve for VAD, we're just going to get positive 9 volts, which is the same answer we got when we did KVL at loop 1. So as you can see, there are multiple ways to solve these problems most times. It's really up to you which way you want to do it. You will always be able to get the correct answer, right? Now, they also want us to find the voltage VCE. So I'm just going to clean up this diagram and move this wire that we added in. And then we're going to draw a wire at the points VCE. So let me just remove this. Okay, now we know we're going to have another wire that's going to be from VC to E. We know this is going to be VCE. This is the positive terminal. This is the negative terminal. We can call this loop 1. We can call this loop 2. Right? So now when I look at this, we have two options to find VCE. We can either take KVL at loop 1 or KVL at loop 2. I'm going to do it both methods once again. I'm going to start with loop 1. So let me just label this part A. And this one down here is going to be part B. So I'm going to say KVL at loop 1. So as we start to walk in, I'm just going to start right here. We're going to walk into this negative terminal, right? So as we walk into this negative terminal, we're going to have a minus 4Vx. Don't get confused with that one, right? We're going to have a minus 4Vx. As we continue, we have minus 1. That's the voltage across this resistor. We know the voltage across this resistor is 2 volts. But because we're walking into the negative terminal first, it's going to be a minus 2 volts. I'm going to write minus 2. And finally, we're going to come around and we're going to have plus VCE. And that should equal 0. Alright, so now we have two unknowns. Now we know this is a voltage-dependent voltage source, and the value of Vx, according to our circuit, is just 2 volts. So we're just going to substitute 2 into this equation for Vx. Minus 4, this is 2, minus 1, minus 2, plus VCE equals 0. Negative 4 times 2 is going to give us negative 8, minus 1, minus 2, plus VCE equals 0. This is going to give us negative 11 plus VCE equals 0. Therefore, VCE equals positive 11 volts. So this is our answer for the voltage across the terminals C and E. Now let's do KVL at loop 2, just for the sake of doing it. Like I said, you could have chosen any loop and you would have gotten the answer correct, right? So let's start at this 12 volt source. When we walk around this 12 volt source, right, we know we're going clockwise. We know we're going to go this way, clockwise. So we're going to have a positive 12. Then the voltage across this resistor is 1 volt. But because we're entering the negative terminal, we're going to write it as minus 1. And we have minus VCE. Equals 0. So we can write this now as 11 minus VCE equals 0. You have negative VCE equals negative 11. Therefore, we can say the voltage across the terminal C and E equals a positive 11 volts. So this is our answer when we did KVL at loop 2, which is the same answer we got when we did KVL at loop 1. As we can see, there are multiple ways we can solve these problems. It's really up to you, but the most important thing is to practice, practice, practice. That's the only way we can get better at these type of questions, and it'll be easier for us to understand.